In our last video, we looked at this term of enthalpy when we were considering whether or not a reaction would be spontaneous. We're going to take this a step further and we're going to discuss what's called entropy today. In combination with enthalpy, we'll be able to make a better determination whether or not a reaction will be spontaneous, right? Will occur without any outside energy or intervention. And we had looked at how an exothermic reaction has a negative change in enthalpy, so energy would be released. And with an endothermic reaction, we would actually have to add energy for reactions to occur, but either or could be spontaneous, depending on this term that we'll look at today called entropy. So what is entropy? You may have had in previous like in general chemistry too, you might have defined entropy as terms like molecular disorder, randomness or chaos of a system, or depending on your textbook, sometimes they refer to these as degrees of freedom. So entropy gives a quantitative value or a numeric value from the different vibrational, rotational, and translational states that a molecule may be in. And every atom, every bond between atoms, rather, has different vibrational energies associated with it. Rotational energy is, due to bond rotation, and then translational energy results from molecules moving through 3D space. So all of these collectively, the vibrational, rotational, and translational, contribute to our values for entropy. So a way that is commonly used to visualize entropy, right? We'll look at this visualization here. We have these two vessels that are separated by a valve that is closed on this side here. And there's some gas molecules that are limited to this side of the glass vessels. And when we open that valve in our second scenario here, we see that the gas molecules can move freely between the two vessels. So what this does is this can increases the number of states, or you might have heard them referred to as microstates for the molecules, because of an increase in volume. When these gas molecules have more volume to occupy, a greater entropy results. Different, the molecules in this case have a larger volume to translate, move around the container now. So a greater entropy overall results. So we would see an example of a positive change in entropy here. But what we're actually going to be looking at is not just the change in entropy for our system, or the delta S system here, which is the reaction itself. We're also going to look at the delta S of our surroundings. This can be, if we're considering a reaction, the surroundings could commonly be the solvent of that surrounds the molecules. So overall, we'll look at the total change in entropy, both what the system contributes and the surroundings. And if that term is positive, we would consider our process to be spontaneous. So again, we don't just look at the change in entropy, but also we would consider a change in enthalpy. And we'll look at that in section 6.3 when we combine these two terms. But the last slide that we want to look at here is, again, just referencing the system itself. And we'll look at two factors that affect whether or not our entropy change of our system is going to be positive or negative. So in these two scenarios, we have here 1 mole of a reactant that converts itself into 2 moles of product. So just the sheer number of 1 increasing to 2 means that we have Avogadro's number of particles more in our product, right? So we have 1 mole, so 1 times 6.022 to the 23rd of reactant, and then we have twice that amount of products. So imagine all the chaos and disorder that would result from having twice this many particles. So that's why we see overall an increase in entropy with this type of reaction, right? When we go from 1 mole to 2 mole in this specific case, but any increase of moles of product. Then we have our second factor down here, where we start with a cyclic structure, a cyclic molecule, which is in a ring form. So it's more ordered than what we see over here with our product, which is an acyclic product. So as a cyclic compound becomes acyclic, we would see a positive increase in entropy. This is due to not the number of molecules increasing, but the degrees of freedom or the microstates that could result, or the increase that could result due to the structure changing its shape. So this is where we'll end today. Our next section, 6.3, will be in our next video lecture.